Hello, I am Professor S. Shankaran in the Department of Metallurgical and Materials Engineering.
Hello, welcome back to our lectures. And if you recall what all we have seen so far in this course, especially in the last class, we discussed about anelasticity. That means time-dependent elastic behavior. So we also looked at some of the examples for this anelasticity nature in terms of thermoelastic effect and diffusion, and there is something called relaxation time, right? So all these parameters we will be using it in the material application and its deformation behavior and so on. Okay. Today we are going to turn our attention to another important concept as the part of introduction and fundamentals to this course called dislocations. Right? Very important idea or concepts, especially in explaining the deformation behavior of crystalline materials. As long as you are dealing with the crystalline materials, and the deformation is only explained through dislocation mediated plasticity. Okay, and if it is non-crystalline material, amorphous material, the things are different. But as far as the crystalline materials are concerned, the dislocation concepts are very important, and it's better to spend some time on this as a background before proceed with the course. That was the intention. I have prepared this kind of lecture. And before even going to the dislocation introduction, and we will spend some more time on an estimate of the atomic bond strength. So we have already looked at different kinds of bond, and we also looked at the definition of what is bond length, bond strength, and different kind of bonding, and etc. So suppose if you theoretically try to estimate how much energy is required to break a bond, the atom to atom bond, how much it would be. So it is a theoretical estimation of bond strength, and what you are seeing in this schematic diagram is well known to you now, because we have enough background for this kind of, what is this curve? This is a force versus distance plot. Several times we have seen this, and the notations are different because I have taken this particular image from the different references, so you don't have to worry about the different notations, but the meanings are exactly the same. Okay, so what you are seeing here, there are two atoms, atom 1, atom 2 here, and the distance between these two normally we denote as a d naught, but in this particular figure it is written as b, and this is the force distance curve, and it can be approximated as sine wave. That is why this extension is given, and this is the direction, the distance from which we are going to pull this atom from its equilibrium position, and then when it moves from this position towards the x direction, it goes through a maximum, and then it comes to a minimum. Okay, so what are the points? The force required to separate two atoms to a distance x plus b increases for increasing x until the maximum cohesive force is reached, at which the total separation results. So x plus b, so this is b, so this is x, so 0 to x. So as it starts moving from here, the force is increasing and it reaches a maximum where the cohesive force is reached. This is xm. This is the position where it is the cohesive force is maximum. After that, the two atoms get separated. The force displacement curve can be approximated by a half sine wave. This is a half sine wave. It's what's shown here. Hence, the force per unit area to separate two planes of atoms is given by sigma is equal to sigma I sine 2 pi x by lambda. The distance here, that is half sine wave, this distance is lambda by 2, and the force per unit area is given by sigma is equal to sigma I sine 2 pi x by lambda, where sigma I is the cohesive force, and we are interested in calculation of this. So what to do for calculation of sigma I? It is necessary to eliminate lambda. Okay, so how do we do that? Let us look at what are the simple terms available with us. For small displacements, sigma is equal to sigma I times 2 pi x by lambda. This is valid. These small displacements are still elastic. Please understand, we are still talking about elastic deformation only. The elastic strain is epsilon is equal to x by b. We are interested in moving the atom to the position of x, and then the actual displacement, original displacement is b. And the stress follows from sigma is equal to E epsilon, and we can replace the epsilon with x by b, then we get sigma is equal to xe by b. Suppose if we combine these two equations for sigma, then we get a different formula. Xe by b is equal to 2 pi x times sigma I by lambda, and lambda sigma I can be written as lambda by 2 pi times E by b. So this is one expression, and we need to eliminate lambda. So we will go to the other part of the calculation. The area under the curve is the work required to separate the planes of atoms. Hence, the area represents twice the true surface energy gamma. You see, when you create or when you break a bond, okay, or a plane, we will see this in much more detail in a fracture mechanics. We will bring these concepts. When you separate these two, when you break an atom, you are essentially creating two surfaces. Okay, so that is why it is given, and it is surface energy gamma is being considered, and which is equal to integral 0 over lambda by 2 sigma I sine 2 pi x by lambda dx. So we can just solve this. It's a simple integral. So what you get is sigma I lambda 2 by times minus cos 2 pi x by lambda to the limits. We can apply these limits 0 to lambda by 2. Okay. Suppose if you substitute these limits, then we get this. So you get finally sigma I lambda by 2 pi into 2, or lambda is equal to 2 pi gamma by sigma I. Suppose if you compare this equation with this equation and compare and combine, what we will get? We will get something like sigma I is equal to E gamma by B to the power half. So this is the expression for the cohesive force for separating the two planes of atoms, theoretical value. So for many materials, surface energy gamma is given by EB by 40, and then the theoretical strength is about E by 6. The problem is this value E by 6 is very, very high. Okay, for example, E normally measured in GPa, right? But in practice, most of the engineering materials or any common material called mild steel, even if you calculate the theoretical strength, it is 200 by 6 approximately. It is 33 GPa, which is phenomenally high, far away from what we get in a simple tensile test. So this is one big discrepancy, right? Similarly, another example, same idea we are trying to give. Suppose if you take this lattice and then this is a shear stress applied in both directions. Just imagine that because of this shear stress, the atom 1 moves from the new position 1 prime and making a displacement delta. Still it is within the elastic deformation. Please understand, we are talking only about elastic deformation. Suppose if you consider this 1 prime atom comes to somewhere in between here, between the 2 and 4, some middle way. That means the atom has reached a metastable position. Okay. But in this metastable position, from here, the atom can move either to this direction or this direction. Either both ways are possible, right? So because at this mid position, you see that the potential energy is almost zero. It has nothing to do. It can go this way or that way. Okay. So if you assume that the displacement or the external force applied, the shear stress applied, is good enough to pull this 1 prime atom to the next position, that is 4, above 4, then the 1 prime atom will have a new neighbor, nearest neighbors. Okay, it may restore the original position locally, but ultimately what happens is that will result in a slip. Crystal will result in a slip because this will move here and this will move here and this will move here, like that. Okay, so that is exactly was shown here. So then also, so that is a variation of shear stress tau and a potential energy V with a displacement. So this is all nicely shown here. Here again, the shear stress necessary to shear the atoms over one another has been calculated to be of the order of 1 into 10 to the power 6 to 2 into 10 to the power 6 psi, pounds per square inch, which is 1 psi is equal to 6.89 kilopascal. So we use this units normally. This is taken from a very old text, so they use this kind of unit system. But again, the experimentally measured values for FCC crystals are only of the order of 10 to the power 1 to 10 to the power 3 psi, okay, which is very, very low as compared to what is being shown theoretically. So what happens is these are the discrepancies, right, in terms of strength, what we actually calculate from theory and what we observe in practice. So there is a discrepancy. So in order to solve this discrepancy, people introduce the concept called dislocations. So what are dislocations? Okay, we will see now. The stresses required to cause slip were measured by tension test of single crystals. G.L. Taylor, Polanyi and Vorovan independently postulated that pre-existing crystal defects called dislocations were responsible for the discrepancy between measured and calculated strengths. So this is a postulation by these three scientists, and they kind of prove that dislocations are responsible for the measured low strength values in single crystals. Okay. So they said that the crystal slip occurs by a motion of dislocations, and many aspects of plastic behavior of crystalline materials can be explained by dislocations. Among these are how crystals can undergo slip, why visible slip lines appear on the surfaces of deformed crystals, why crystalline materials become harder after deformation, and how solute elements affect slip. So these are some of the questions they try to explain, looking at the dislocations behavior. Okay, so that's why studying about dislocation is important as long as you deal with crystalline materials deformation behavior. Okay, so now we will slowly see what is a dislocation, and first we look at the geometry of dislocations. So this is a nice picture of schematic of dislocation, which is called edge dislocation. You see that you have the view of atom columns and you are looking it from the front, and what you see is these are all atom columns. They are all connected by the kind of springs, and you have that extra plane got inserted in the middle, and this is called edge dislocation. This kind of a geometry is called edge dislocation. One special form of dislocation is an edge dislocation shown here. The geometry of an edge dislocation can be visualized as having a cut part away into a perfect crystal and then inserted an extra half plane of atoms. So what it means is it looks as if this particular plane was cut from somewhere and got inserted from the perfect lattice. It gives that impression like that. The dislocation is the bottom edge of this extra half plane. So this is an extra half plane, and this is where the dislocation core is there, and this is a bottom edge. The other schematic shown here is also showing the edge dislocation only, but it gives a little more information. What are the other information? There is something called B here, that something marked B here, and there is a symbol for this dislocation, edge dislocation line. Okay, so the edge dislocation line is here. So we will see what is this line. So because we are seeing it from the front, and this picture shows much more detail, even though it gives a similar information, but more details can be found here. What is the more detail you are seeing? So this extra half plane is inserted here. This is a whole crystal, and this extra half plane is moving in a plane called a glide plane or a slip plane. So this is a plane, and then you can see that this symbol is the edge dislocation symbol is here over here. That means this whole block is tilted here, and then you are seeing the dislocation line. So the dislocation line is going through the plane of this slide. Okay, it is going perpendicular inside. So that is what's shown here. So that is called dislocation line, and this is an extra half plane. And wherever the crystal got slipped to a distance which is B, called Burgers vector, also called slip vector, is shown here. So extra half plane of atoms inserted in a crystal structure is a typical description of edge dislocation. The another important observation is B is perpendicular to dislocation line. So in this geometry, the Burgers vector is perpendicular to dislocation line. So you can see that this is B here and this is a dislocation line. So this is perpendicular to this. So these are all the very important characteristics of edge dislocation geometry. The next one is screw dislocation. Okay. So you can see the nice schematic here. The huge block got slipped, and what you are seeing is that both of them are same, but one is in the side view, the other is in the top view. So you are looking at from here, and we are looking at this from here, this side view, and this is from the top view. So as the name implies, the crystal block has got displaced in a kind of a screw axis here. Okay, I will explain this in much more simpler way in a couple of slides. So here the displacement is measured again by a Burgers vector B, and then here you see that it is the crystal has slipped. Okay, whatever the B here, it has moved and it would have come out of the other end. And you see the dislocation line is here. It is shown here. And for the better view, the B is shown here. And I will explain this a little more by taking up this additional schematic. This is a unslipped crystal unit, and this is a slipped crystal unit exhibiting a dislocation line. Okay. So here you see that this is shear stress applied in the top and bottom, and as a result the crystal has slipped, and you see that the slip vector is here, which is equivalent to Burgers vector B, and this is a glide plane. You just compare this glide plane with what is shown in a edge dislocation, and this is the dislocation line. Okay, so the dislocation line is here, which is with respect to B, it is parallel. Okay, so this is one of the characteristics here. So screw dislocations can be visualized as a spiral ramp parking structure. So it is some analogy, parking structure. You can think it's a huge structure you can example. One circuit around the axis leads to one plane up or down, whether it is a positive screw or a negative screw, right? Planes are connected in a manner similar to the levels of spiral parking ramp. Okay. And of course, this spiral planar ramp resulting from a shear deformation. The Burgers vector B is parallel to the dislocation line. Can we check this? So what is dislocation line here? So this is dislocation line, and this is slip vector. This is parallel to this. So B is parallel to dislocation line in a screw dislocation geometry. B is perpendicular to the dislocation line in an edge dislocation geometry. These are all the important points to keep in mind. So Burgers vector B is a measure of lattice distortion. So this is also is a measure of lattice distortion, not just describing individual dislocation alone. And why the name screw dislocation? Because as I just mentioned in the previous slide, if you take this cylindrical body, and what it's shown here is a screw dislocation with a Burgers vector B here, and suppose if you try to continue this displacement here as per the screw, it will go in a positive direction of and make the cylinder as a screw. Completely it will become a screw. The path of this the glide will be in a spiral way, and this rod will become like a screw. Okay, so that is why it is called screw dislocation. And similarly, yeah, so this what is this arrow around this? This is called Burgers circuit. How do we do that? We will see in a minute. And we do it in a clockwise direction, so it is a positive sense, and we can also do it in a anti-clockwise, then it will be a negative sense. Okay, so this is called Burgers circuit. And what is the next? Edge, screw, and mixed dislocation. We are not just going to stay with edge or screw geometry alone. We are also going to have a mixed dislocations. If you look at the schematic here, it is nicely shown that this is a screw dislocation in this end, and in this end it is edge dislocation. Okay, so edge character and then screw character completely 100%. And what about the mixed one? Where do you find? Somewhere in the middle. How do we understand this? So you look at this top view again. So this is a pure screw dislocation, and this is a pure edge dislocation here. And somewhere in between it is B. Still, it is very difficult to understand from this image, because it is the displacements are not they are shown here but not clearly. We will take up some assistance to explain this, some more schematic. So what you are seeing here is, this is a crystal which is slipped here in this direction, A, B, C, and the force is applied in this direction. So the crystal, part of the crystal slips here, and then it has both screw as well as edge. Okay, so if you look at from the top, so this is how it will look like. So this schematic will be very simple to explain now. Imagine that this is the AC line, which is marked in a dotted line here, which is now drawn as a full thick line. So A, B, C. So if you compare this geometry here in a 2D plane, that is top view, and what you see here is dislocation line is curved like this. So this is screw dislocation, which is parallel to B, and this is a dislocation line which is also parallel, and it comes and ends here. The dislocation line is perpendicular to the B, that is edge character, but somewhere in between it will be a mixed dislocation. So how this B and line will orient? Obviously, when you say mixed, you should anticipate that the B should have some angular relationship with the dislocation line. So how do we understand that? So this is the dislocation line, and this is a Burgers vector. So if you just take the two components, the angular components, right, it will have some angular relationship, right? So one is edge and another is screw. The screw will be, suppose if you make this triangle and this is an alpha angle, then it is B cos alpha, a screw component, or B sin alpha is an edge component. So that is how you should look at it. A mixed dislocation will have both the characters of edge as well as screw dislocation, characteristics, and that can be understood by this.